Thank you for the introduction. First of all, I would like to thank the organizers for giving me an opportunity to visit this nice place and give a talk here. I think this is the first time for me to come to UCLA. Somehow, UCLA is very, very well known in Japan. So it was a kind of a little bit of a dream to come here, and I'm very happy to be here. And another reason I'm happy to be here and to give a talk here is that after spending 3 days during this conference, I have been realizing that I'm not sure if I have really worked on Vertex models. Usually, I have been working on some continuous time processes, so I'm a bit wondering, but there's some connection. So still, yeah, I'm very happy that the organizers included me as a speaker. I'm very happy. And some people told me during the workshop, some people told me that the design of my shirt looks a bit like some tilings coming from the Vertex model. So, yeah, so at least I wanted to show some respect to Vertex model by wearing this today. Okay, anyway, sorry, this is just a joke. Sorry. Anyway, so I'm going to talk about this. So this is today's talk is based on a few collaborations with Takashi Imamura from Chiba University, Matteo Mucciconi, who was my former student, but who is now working at the UK, in Warwick. And Travis Scrimshaw, he's from California originally, I think, and spent a few years in Australia, and he's now working in Japan. So kind of main part of the talk is based on this paper, which appeared in Forum of Mathematics last year, but the preprint already appeared 3 years ago. So some people from the audience already know some part of it, but yeah, I will try to provide some new thing towards the end of the talk based on this one, which was supposed to appear before this workshop, but we are still trying to finish it. Anyway, okay, so yeah, so still, yeah, today I feel I should start from the Vertex model. So, but still, I usually prefer to work on some stochastic processes, and let's start from stochastic 6-vertex model, which already appeared in some talks during the workshop. So yeah, so we give 6-vertex ways. So for stochastic case, they should satisfy a certain probability condition. So we have 2 parameters like this. And as you know, if you take certain continuous time limit, then this becomes the well-known ASEP, continuous time ASEP, standard one. But some of you should know that we consider certain special cases of this stochastics, or more general 6-vertex model in which one of the weight becomes 0. So for example, in this stochastic 6-vertex case, either if we take delta 1 equal 1 or 0, delta 2 equal 1 or 0, so then one of the weight becomes 0. So then the 6-vertex model reduces to 5-vertex model, right? And in kind of stochastic language, this corresponds to TASEP, totally asymmetric exclusion process. Okay, which is also very important in my talk. But somehow kind of background question in this talk is the following, I think. So a 6-vertex model, free fermionic? Of course not, right? So, except when you take data equals 0, so 6-vertex model is, of course, considered to be non-free fermionic. But as some of you or many of you may already know, so TASEP, which corresponds to stochastic 5-vertex model, is very much related to free fermion. There are some determinant structures. So maybe one question. So in your opinion, is TASEP a free fermionic model or not? Yes, TASEP is a free fermionic model? Okay. Oh, no, so TASEP is still not free fermionic model. No, not quick. So there seems to be some discrepancy, a bit interesting, I think. But for ASEP and the general data, of course, they are not really considered to be free fermionic. But still, so for people who have been working on KPZ type models, people know that after some calculations, we can arrive at some determinant formula for important observables, right? Like height, generative function of the height. So in that sense, ASAP is very much related to free fermion somehow. And my talk is to try to have more kind of explicit way of understanding this appearance of free fermionic nature of the problem, in particular ASAP case, ASAP or higher spin vertex model, stochastic higher spin vertex model case, by using some bijection related to RSK. So on Monday, there was a nice talk by Filippo about non-stochastic six-vertex model. And of course, this is not really free fermion, probably, but he also uses some very nice determinant formula to do asymptotics, right? So maybe there's some connection. If there's some connection, there are many nice, interesting questions, I think. But in my talk, I basically stick to stochastic case. Yeah, so I'm not sure that this book was translated to English, but in Japanese, in Japan, there's a book written by Michio Jimbo about holonomic quantum fields. When I was a graduate student a long time ago, I was reading it, and this is basically about Ising model, right? So free fermionic case. But towards the end, there are some commentary remarks, and there he talks about more general integral system, in particular six-vertex model. And there's a comment that there's a huge gap between free fermionic models and non-free fermionic but integrable models. And experts know this fact from the bottom of their heart, or something like that. I was very intrigued by this comment. I'm still working on understanding his comment, I think. Anyway, so this is the plan of my talk today. So first, I talk about kind of basics, because I heard from Jan that there are kind of two groups of people. One group is from stochastic side, basically. The other is from equilibrium stat mech side. So yeah. And for people from stochastic side, this story you know very, very well for more than 25 years, so you can take a nap. But, for those from the other side, some basics may not be so well known, so let me explain that. But then I mentioned a little bit some known facts about other more generalized KPZ models, typically with parameter Q, and which is related to q-Whittaker or McDonald measure, thanks to Alex and Ivan's work, and a few others. And then so my talk is about a kind of, there's a relation between q-Whittaker measure, which it does not seem to be related to free fermion, and the periodic Schur measure, which is a generalization of Schur measure, which is kind of determinantal or related to free fermion. Right? So there's some connection between non-free fermionic thing and the free fermionic thing. And recently we found a bijective way to understand this connection. Right? So this is the main subject of my talk, and this is this part. Hopefully I can explain a little bit about some details of the proof, but let's see. And as a kind of new aspect, for those who know this already a bit, towards the end I'd like to explain column version, different version of the Skew RSK dynamics, which shows some nice connection to BBS, which also appeared in the talk yesterday. BBS is a box and ball system. Okay, so let's start from the TASEP case, which is kind of well known for 25 years now. So TASEP, in my opinion, I'm still thinking about, not from the language of vertex model, I'm thinking about some process, right? So let's consider one-dimensional lattice, and so, each side is occupied or is empty, and each particle tries to hop to the right neighboring site with probability 1 minus r. And there's exclusion interaction. This is one version of discrete time TASEP. And there are many quantities of our interest, but one particular thing is to consider the integrated current at the origin, the bond between sides 0 and 1. So we just count the number of particles which cross to this bond. And if often it is useful to consider a particular initial condition, like this step initial condition. So then this integrated current is just the number of particles right half of the space at time t. And there is a simple mapping from TASEP, or this particle configuration, to height configuration And so aseptic dynamics can be translated to certain stochastic surface growth model, which is in the KPZ class. And in this height growth, surface growth language, so integrated current is just a height function, which also appeared in many talks during the workshop. So we are interested in statistics of that. Okay, so this is 25 years ago now. So due to very, very nice breakthrough work by Johansson, there's a nice, maybe this part may not be really due to Johansson, but sorry. So there's a nice mapping from the problem tacit to some combinatorics, right? So we are using step initial conditions. So this is space and this is time. So these are the trajectories of particles starting from the step initial condition. At the beginning, there are particles here. And the first particle has to hop to the neighboring site after some waiting times, right? Like this. Then, so the first particle is free. So this is independently doing some discrete time random walks only to the right. But the second particle has to wait until the first particle hops. But after that, he can, like this. Then we can focus on the waiting times of this geometric, the waiting time is geometrically distributed, and we can focus on the waiting times of ith particle, maybe jth hopping of ith particle, something like that. This may be written as Wij. Of course, this is IID random variable, geometrically distributed. The parameter of geometric distribution is R in this hopping probability here. So then, maybe as a sample of Wij, maybe there's something like this, right? And if we are interested in the current at the origin, we can focus on this just n by n square matrix, where so n is like this. If we are interested in the probability that the current is bigger than or equal to n, we can stick to n by n square matrix. And obviously, the matrix elements are non-negative integers. Okay, so then the information of the current is also encoded nicely in this language. So one can consider some upright path starting from 1, 1 and arrives at n. And then, so for each path, you can associate some kind of energy just as a sum of Wij's, but maybe you can maximize the value. And this may be called Gn. And then one can see that the distribution of nt is the same as the distribution of Gn. So rather than considering n, we can consider Gn in this language. Right? Is it okay? Okay. So then comes this RSK. RSK means Robinson, Schoenstedt, Knuth, 3 names. So there's a nice correspondence between this kind of integer valued matrices and a pair of Young tableaux whose entries satisfy the semi-standard condition. Semi-standard means that so this kind of shape is called Young diagrams. You can fill the numbers. And for semi-standard Young tableau, they should satisfy certain increasing conditions. So for downwards, they should strictly increasing. To the rightwards, they should be weakly increasing. This is the condition for semi-standard tableau. Right? So, and there is a bijective correspondence between this kind of integer matrix and a pair of skew tableau. Semi-standard tableau. And in fact, there's a nice algorithm to show this bijection. So at an intermediate step, maybe one can think of this kind of bi-walls, generalization of partition matrix. So they are representing the matrix elements of this matrix. So this is also bijection, very simple bijection. So I'm writing 1, 1 means that I'm looking at 1, 1 element of the matrix. And this is 1, so I write 1, 1 just once. Now I look at this. This is 1, 3 element. So this is 2. So we write 1, 3 twice. Right? Like this, then we write 2, 2 twice. 3, 1, 1, 3, 2, 1. So this is in bijection, right? Is it okay? Okay. So then there's a nice algorithm due to RSK to see a pair of skew tableaux, to construct pair of skew tableaux from this byword, right? So this is consisting of what are called insertion and bumping. So maybe so this is an example for this case. So first, maybe we look at this downside of this byword. So we create some semi-standard tableau by using these numbers, 1, 3, 3, 2, 2, 1, 2. So they are appearing here. So we start from empty situation, and then we put 1, because the first entry here is 1. So like this. Then we put 3. So then, as long as they satisfy the semi-standard condition, they just they are added to the right of the existing tableau. So this 3 just comes here. Sorry. Okay, 3. And then the next one is again 3. So this also comes here. But then we have to do something because of 2. Now 2 comes here. But if you put 2 here, then it destroys the semi-standard condition. So then, to satisfy the semi-standard condition, maybe we can think that 2 bumps this leftmost 3 to the next row. So then 2 comes here, then the 3 comes to the next row, and then it goes all the way to this leftmost part. In this way, you can create a semi-standard tableau starting using these numbers. So this is called P tableau. And the Q tableau is constructed from these. So you just put these numbers where these tableau has increased during this process for P. So then this becomes also semi-standard tableau. So then in this way, from these or from this matrix, you can create a pair of semi-standard tableau, right? And this is RSK algorithm, and this is not bijective. Okay, so this is the basic version of RSK. Is it okay?
Why does the last 3 go down in the third row?
Sorry?
In the Q tableau, why does the last insertion of 3 drop down into the...
3?
No, sorry. Wait a minute.
Yes.
Can you explain the rules for constructing the Q tableau?
Q tableau.
The same?
So we use these numbers. So first, so you look at where the tableau diagram grows. So this part 1, so this part 2, this part 3. So we just use this order. And then this part grows, so we put these 2. This part grows, we put 2, and so on. Was this? Sorry. Okay. Okay. Is it okay? Okay. Let's go. So then now we have something related to semi-standard tableau, and there's a nice combinatorial formula for the Schur function. So you just consider some polynomials, a1 to the power number of ones in tableau, and so on. So for example, in this case, we consider a1 squared, a2 cubed, a3 squared, right? But there are various possibilities of semi-standard tableaus. So then you take a sum of all possible tableaus. So we have some conditioning on the entries, right? So we are considering entries from 1 to n, something like that. But then this becomes, this is some polynomial in a1 to n. And if you take all sum here, then this gives you the Schur function. So then, by using this mapping, RSK, if we take a sum of all possible tableaus for both P and Q, this should correspond to considering all no-integer matrices here. So then for arbitrary AI and the BJs, so if you take a whole sum, you get some nice identity. And this is written this way. So this is from P and Q, and this is from the integer matrices. And I was getting, I got these matrices from the waiting times of TASEP. In that case, geometric parameters of the geometric distribution was R for all ij's. But now we are considering a generalized situation where geometric variables wij, the parameter is ai times bj. But we can think about such a generalized TASEP. And in this case, yeah, if we take a whole sum, we get this nice identity for the Schur function known as the Cauchy identity. Okay, but we can prove this in a bijective way by using RSK. But because we have a bijection, maybe we can, even if we put some certain condition, then we can still consider such a sum. And maybe I didn't mention, but the current, or Gn, corresponds to the length of the first row in the Young diagram. So considering the probability distribution for current is equivalent to putting certain condition. The length for the length of the first row in the Young diagram. So then we can consider a partial sum of this the product of Schur function with this. Of course, this cannot be completely factorized as in the Cauchy identity, but we can consider, now we are considering a certain measure between like this, and then we are putting some conditioning on lambda 1, right? But for Schur function, there's a very nice different formula called Jacobi-Trudi formula, which allows us to write S lambda just as a single determinant. So this measure, Schur measure, is in the form of the product of two determinant. So this, which is very much related to free fermion at 0 temperature, like in the GUE case. So yeah, from this fact, we can see that Schur measure is a determinant point process related to free fermion at 0 temperature. Right? So this is the old story due to Johansson and several others. Okay, so in this sense, TASEP is almost free fermion, but it depends on how you think. Anyway, so soon later, so Baik and Reis consider a symmetrized version of the problem. So instead, if you consider symmetric matrix, put a symmetry for this matrix, then P and Q becomes the same. And there is a similar identity like this, little identity, and one can consider KP TASEP on the half line, like this. Okay, so this is the basic part. Then, so this has been for the TASEP with Q equals 0, basically. But after that, after 10 years or so, there has been many, many works coming from the KP's equation. For more general case of models like ASEP, something called Q-TASEP, and then comes stochastic higher spin 6 Vertex model. Basically, so these almost all models are kind of degenerate version of a stochastic higher spin Vertex model. So yeah, in that sense, my talk is really about Vertex models. Okay, and today I don't talk about this, but as a generalization of connection between TASEP and the Schur measure, so these people, there are several arguments showing the relation between these KP's models, particularly typically with the parameter Q, to some version of McDonald measure. In most of them, some of them are related to q-Whittaker measure with the t equals 0 in the McDonald, or the ASEP is in fact more related to what is called whole little root measure, which is the q equals 0 case of McDonald. Anyway, so I don't explain this today, but there's a connection between q-TASEP and also KPZ models with parameter q and the q-Whittaker or whole little root measure. So if we can study some certain aspects of the q-Whittaker measure, whole little root measure, then we can study KPZ models, right? And one particular version of the model is the q-push TASEP, introduced by Leo and Matveev almost 10 years ago. and which has a nice property in the sense that so this model is directly related to kind of standard q-Whittaker function, right? So with just n variables and m variables like this. Others are related to different specializations of the model. And yeah, B mu is here like this. Okay, so then as in the case of T-SIP, so in this case, particle position is more or less like a height function or a current, and so this quantity, kind of observable for Q T-SIP, is directly related to the length of the tableau in this q-Whittaker measure. Right? So then we are interested in statistics of this mu1 for q-Whittaker or Hurley-Root measure, basically. But the important difference from the Schur case, T-SIP case, is that there's no Jacobi-Trudy type formula for q-Whittaker function. So apparently this is not at all related to free fermion. This compared to the case of the compared to the case of T-SIP. Okay, but there's some connection to a different measure which is related to free fermion. And this is another generalization of the Schur measure called periodic Schur measure. Some people call it a bit differently, but yeah, I call it periodic Schur measure. This measure was first introduced by Alexei again. And so this was studied in a different language, more in the language of free fermion by Bethe and Boutier. So yeah, I'm citing these two. So the measure itself looks like this. So instead of the usual Schur measure related to T-SIP, we consider skew shape now, right? Instead of only S lambda, we are considering lambda over rho. And we are basically interested in the statistics of lambda, so we may take sum over rho already. You could think about the measure before taking this, but yeah, we consider the case after taking sum over rho, empty sum. And this is not directly determinantal, but if you consider kind of so-called shift mix version, kind of grand canonical version of this measure, by using this random variable S distributed according to this rho, where theta is a theta function. So then one can see that, so they showed, Alexei and these people showed that this measure with this shift mix is a DPP, determinant point process. But then the kernel showed some relation to free fermion now at a finite temperature, not at zero temperature. Today I don't really use this formula. So for the Schur case, the measure was really just a product of two determinants. This is related to zero temperature free fermion. But for this case, we get some, infinite sum of the two function, which is multiplied by what is called a Fermi-Dirac distribution function. Then this shows a connection. There is a relation to finite temperature free fermion, but I don't use this today, so I'm not writing that. Okay. Anyway, so there's a nice relation between the statistics for the length of the first rows of the two measures, q-Whittaker measure and the periodic Schur measure. As a statement, it's like this. So on the left-hand side, we are considering q-Whittaker measure, and we're interested in statistics of mu1, but instead of really considering distribution function, we are considering particular expectation observables related to mu1. So this is for the q-Whittaker thing, which is apparently not free fermionic, right? But in fact, there's an identity saying that this quantity is nothing but a probability for the lambda 1, maybe plus S. And on the right-hand side, we are considering the periodic Schur measure, which is related to zero temperature free fermion. So in that sense, there is a relation, right? But this kind of formula can be shown by comparing some formulas, right? So after doing some calculation for q-Whittaker measure, one can arrive at the Fredholm determinant type expression. And so on the right-hand side, this is free fermion. Naturally, there's a Fredholm determinant expression. One can compare, and one can check that they are the same, right? So in that sense, one can check this identity by this, but what we have found recently in the paper I'm trying to explain from now is that there's a more bijective understanding of this identity. Okay, so yeah, so in this way, this is just expectation, the probability, but maybe we can rewrite this identity in the language of special functions. q-Whittaker functions and skew Schur function, then yeah, if you just rewrite this more explicitly, then this is the identity equivalent to this identity. So then, yeah, so we want to understand this identity in a more bijective manner. Okay, so this is the kind of main part for those who haven't heard. So we want to make certain connection between q-Whittaker thing and the Schur thing, right? So maybe Schur function seems easier to consider. So let's start from that side, skew Schur. As in the case of usual Schur function where rho is empty, so there's a nice combinatorial formula as a sum of a semi-standard tableau of a skew shape now, like this, for the skew Schur function. So if you consider a skew shape and put certain numbers, take a sum over semi-standard tableaus, then you get a skew Schur function. This is a combinatorial kind of definition formula. Okay. So for those who are not really, so yeah, so now I'm considering here, right? So there's a combinatorial formula for this. Maybe we are considering some combinatorial object related to right-hand side. We want to make some connection to some combinatorial object related to the left-hand side. Okay, we were, yes. I'm just reading this basically. So first, we can do rather simple procedure for a pair of skew tableaus. Let's use this particular example. So these are pair of skew tableau, right? First, we can try to kind of squeeze the pair of tableau a little bit.
Where did the pair come? So I see there's one tableau that defines this S lambda. Is the pair because you have a product of S lambdas?
Yes, yeah.
But then why do they need to have the same
shape?
The same skew shape. They have the same exterior shape.
What do you mean? So this
you're
this
saying
is really in the,
yeah. Okay, both
yeah. So this is really like a usual RSK, yeah. So somehow the bijection gives you the pair of skew tableau with the same shape, skew shape now. Okay, so we try to squeeze this tableau to the left as much as possible, but in such a way that they still remain semi-standard tableau. So these two, so maybe we can shift just by one. We can do the same here, but if we try to do it once more, so then it becomes non-skew shape. So we stop at that point. Okay. So we can squeeze these tableaux just for the first two rows of this tableau by one step, right? So then we get, in general, we get some partition after squeezing. The squeezed part becomes partition, which is called nu. Right? Okay. So then we now introduce this what we call the Skew RSK map or the dynamics. So I already explained for the kind of usual case the insertion and the bumping, right? For our case of Skew RSK, we have to introduce slightly different procedure called internal insertion, which was originally introduced by Sagan and Stanley in 1990. So let's start from some skew tableau like this. Then, so we look at certain corner of these non-empty boxes. Then, let's suppose that we pick up this 2. We could pick up something else, but let's suppose that we pick up this 2. So then, internal insertion means that somehow, once we pick up this, then we just do kind of bumping. We suppose that this is bumped, right? In the original case, bumping should appear when we insert, and when this does not satisfy semi-standard condition. But now we are considering another mechanism in which this is kind of bumped to the next row. But then after that, it's the same thing. So 2 is somehow bumped. Then we do insertion, and the 3 is bumped here, and so on. Right? Okay, so this is for one tableau, but now let's consider some procedure for a pair of tableau, which was coming from the previous page. So then, now we have these. First, we look at this Q tableau, and look at the number 1. So now in this example, 1 is here. So then we decided to do this internal insertion at the corresponding place in P. So then this is exactly the same. So after doing this internal insertion at this place, the P tableau becomes this. This is they are the same thing. And for Q tableau, so this part goes away, and then we decrease all numbers, the entry of the number entries by 1. So these 2 becomes 1, 3 becomes 2, and so on. But 1 should become kind of 5. We are using a periodicity, and then put it here, where this increases, like a bit in the case of usual RSK. So this is a map from a pair of Skew tableau to another pair of tableau. Right? So this we call iota 2. There is a very similar procedure to iota 1, but we are calling this iota 2. So we are now thinking that something like parameter n is 5. So the possible entry, the number of the entries are up to 5. So here we are kind of making the change of the number of the entries. But if we do this n times, then the ordering becomes the original one, right? So this procedure is defined here. And this is something we call the Skew RSK map. So this is just an iteration of this iota 2 map n times. So this is still, of course, a map from a pair of Skew tableau to another pair of tableau. And in this example, so we get this pair after 5 times of this iota 2. And this is what we call the Skew RSK map. This is still a map from a pair to pair. We can still iterate this procedure many, many times, right? Starting from some initial pair of tableau. So this is something which we call this Skew RSK dynamics in the title of my talk today. So this is just, so P and Q at time t plus 1 is defined by application of the result of application of Skew RSK map for 2 PT and Qt. Yeah, so this is our initial pair of tableau, and we apply this RSK maybe 10 times, many, many times. And after 10 times, what you observe is that something interesting now. So this is just a consecutive application of RSKs, but after a certain time, it shows interesting behaviors in the sense that even though there are some interactions among columns, if we wait long enough, each column becomes kind of independent, right? So now after 10 times, this is almost visible. So the first column has only 3 non-empty numbers. This propagates with definite speed 3, right? And for the second and third, they're already kind of separated, and they are just propagating with speed 2. And this propagates with speed 1, or like that, right? And this is a kind of general phenomena. And then, so one thing we can do at this point is that after looking at this asymptotic behavior, then we may be able to forget about the empty parts, then just read the non-empty numbers, then create some kind of pair of tableau. Of course, we are now neglecting empty parts, so they are no longer usual semi-standard tableau. But of course, in each column, they are increasing. And among columns, there are no conditioning, right? So we are calling this, there are certain names, it seems that we are calling this vertically strict tableau, VST, of shape mu. After this procedure, we get VST of the same shape. Okay. And as some of you should have observed, so the behavior of this Skew RSK dynamics is very much similar to the box and ball system, right? So we have certain initial conditions. After a while, it becomes separated into solitons. And something very similar is happening here. So this part was explained yesterday by David. Okay, so now the question was, is there a real connection to q-Whittaker measure? And so this part took some time to realize. But in fact, there is a nice formula for the q-Whittaker function as a sum of VSTs of a given shape. Yeah, it was written in a slightly different language, so it took some time to notice. But in fact, in our language, if you take a sum of this shape, of this form, with a certain weight here for each VST, then if you take a sum of all VSTs, then this is nothing but the q-Whittaker function. Right? So the H for V is what is known as an energy function introduced by Nakayasuki and Yamada. And this kind of measures the distance, how VSTs is different from the semi-standard tableau. But there's a more precise definition, but okay. And the trivial remark is that Q equals 0 corresponds to Schur case. Okay, so now maybe it's a good timing to recall our identity we wanted to show. So this is the identity. So we started from combinatory object here. And after in this Skew RSK, we see VSTs, pair of VSTs. So if you take sum of VSTs, that produces P mu. The remaining question is how we can get this coefficient and how this energy function appears in this combinatorial map. Right? Okay, so but anyway, so at this point, let me state our bijection between a pair of skew tableau and kind of quadro 4 objects, pair of VSTs, and the new is the kind of the partition appearing in the squeezing and the extra information cap, what we call the kappa. This is explained here. So this is a little bit complicated definition, but so this kappa is an element of the set which satisfies conditions like this. If you write down this shape of mu, you can understand some kind of meaning. But anyway, so there's a set related to this extra information. And then what we could prove is that there's a bijection between these two. And in addition to that, so they satisfy nice kind of weight preserving property written down here. So for the skew shape sites, there's a number of empty boxes written like this. And then after the map, so this becomes the sum of the energies for V and W's, and then the kind of size of that partition and this object. So then now you see that how H appears from the skew Schur side to q-Whittaker side. And so this sum of kappa for this set K, this gives you, one can check, this is not too difficult, one can check that, so this gives you B in front of the q-Whittaker measure. And okay, so this part is even more simple. So for this squeezed partition, you can calculate this, and this gives you another part of the identity. Anyway, in this way, we could prove the identity. Right? Okay, so this is a remark here is that, so they are all related to Cauchy identities. For Schur case, I already explained. So our bijection gives the kind of bijection to q-Whittaker measure, the Cauchy identity in a bijective way. And for Skew Schur, there was already a proof by Saga and Stanley. So by combining these, our bijection and their proof for this, then we can say that now we have found a bijective proof of the Cauchy identity for q-Whittaker. But now we have proved this in a bijective way. So as in the case of Schur, we can consider a kind of restricted sum where we put certain conditioning on the length of the the length of first row, for example, which is related to some certain interesting observable in KPZ models. Okay, yeah, but this I don't do here. Okay, so as in the case of a Schur, where the Bicam rays considered the Schur case, we could also consider the symmetrized version. So then there's a nice identity, which will turn out to be known due to Warner from Australia. And but because now again we are considering bijection, so we could write down certain identity with certain restriction on the length of the diagram. Then it gives you some nice identity between partial sum for single q-Whittaker function and similar partial sum for the Scrimshaw function. So this part is considered to be kind of non-free fermionic related to KPC model, but now this is related to something related to free fermion, right? Now it becomes easier. So now this is related to more Pfaffian rather than determinant. But anyway, so this is our application to the KPC models in House space, which I don't explain today. So, okay, but yeah, maybe I cannot really explain this part, but still, let me still try to make a few comments for the ideas of proof. So, yeah, so first, we realized the identity at the level of determinant. We wanted to find the bijective proof. So we first worked for some certain examples, and there seems to be some nice connection, but proving some properties, bijection, was very difficult, in fact. And so RSK is nice, but it's very combinatorial and it's really complicated, at least for us. So then we are looking at some and considering several ideas. And then at some point, we noticed that, in fact, we are saying RSK, but the algorithm I explained is basically due to Schoenstedt and Knuth, right? Well, what about Robinson? And in fact, Robinson's algorithm is quite different from the Schoenstedt Knuth algorithm, as I explained. Insertion and bumping, they are basically due to Schoenstedt and Knuth, right? So Robinson was using a rather different thing. And in fact, now in the language of modern language, it can be understood as a kind of nice application of crystal theory, in which first he maps the kind of general tableau to kind of standard one, and do something, and then understand the property for the general element, right? We thought that maybe this is a good idea. Maybe we can try to generalize this kind of basic idea to our case, and it worked basically. So in our case, we had to use affine crystal, and in fact, we kind of a representation for affine crystal, which had been known, was not completely fitting well to our scheme, so we had to introduce some new kind of new representation of the affine crystal, but it works, and we could arrive at a bijection, right? So in fact, we are calling this we introduced something called VST, but in fact, this can be identified with a certain type of crystals. Today, I cannot really explain in the end. Kirillov-Leshetin crystal, and then there's something called casual operators, which is a kind of degenerate version of the usual E operator and F operators for SL2. And now we have an important thing is that in our case, we are considering affine crystals. So there's something called E naught and F naught as well by using what is called promotion operator. This is related to kind of periodic symmetry of the affine crystal. Anyway, so this is one. Then, so we can write down some kind of affine crystal graph. And these are classical crystals graph, which are not completely connected. But if we go to affine, they are all connected, meaning that if you consider affine, this kind of tableau with the same shape, they are all connected, right? If you start from particular case of the tableau, there are some paths from there to kind of standard one. So this is already a bit related to the original idea of Robinson. In the affine case, by using zero arrows, we have a connectiveness. And in this language, we can also define precisely the energy function. And then, so we can define the affine crystal actions to first for the set of VSTs and then for the set of semi-standard tableau. And the most important property of these casual operators is that they completely commute with a Skew RSK map. So these are the symmetries of a Skew RSK. So we are considering some time evolution of the general pair of tableau, which looks very difficult. But maybe if we can first apply the casual operator to the standard object, and then see what happens for the standard object for this dynamics, and then try to translate back to the original one, right? But in fact, one can see that for this standard tableau, our Skew RSK becomes linearized. right? So this part, you still have to work, but not too difficult. Then by using these Schur operators, we can really linearize our Skew RSK dynamics. So then, yeah, we can consider many things. It's a bit like a classical integral systems, right? So you're considering nonlinear equations, PDEs, which looks quite difficult, but by using Lux pair or something, you can linearize. And after linearization, things become so simple. And the basic idea is the same. So Skew RSK dynamics is like classical integral system. So we can try to find some linear map of the linearization. And in our case, these Schur operators gives us the linearization. And after linearization, yeah, the dynamics to linearize, it's easy. Okay, let me mention 2 minutes. Okay, 3 minutes for the a little bit new development. So this is the kind of, we are using what is called a raw version of the RSK, but so one of the things we recently did is to consider a different version, column version of the RSK. We thought that this is quite simple, but it contains certain difficulty. But anyway, we have almost overcome them. So we have been considering VST, vertically strict tableau. There are certain conditions, each column, the increasing. But now instead of that, for column version, we consider, horizontal. There are certain conditions for each row horizontally, weakly increasing, but there are no conditioning, right? Kind of dual version of the VST. So we are calling this horizontally weak tableau. And for some, it may be obvious, but this is related to modified whole literate polynomial. Not the usual one, but the modified version. And rather big difference from the previous case I explained is that in the previous case, the dynamics looks quite similar to BBS, box and ball system, but there are some differences. And after applying Schur operator, it was linearized. And then we've got some questions. What is the relation to the linearization of BBS and so on, that we are not so sure. But while considering this version of our Skew RSK, we realized that in fact, after applying similar procedures, then we arrive at something which is exactly the box and ball system. After applying Schur operators, in this case, the dynamics is not really linearized. It becomes BBS. But for BBS, as explained yesterday as well, so there's a non-algorithm, another algorithm called KKR, Kirchhoff-Kirchhoff-Schichten algorithm, which allows you to linearize the BBS dynamics, right? Then we can kind of simply use this KKR algorithm to linearize our original column version of RSK, and then try to prove something. And on the way, technically, what was most difficult is that in the case of q-Whittaker function, there was a kind of known formula. If you take a sum over VST, then it was a q-Whittaker function. And this is related to the fact that the crystal graph, which I was not really explaining, is very much related to what is called de Mazur crystal. And for this, there's a nice sum, and this gives you q-Whittaker function. This is known. But for this case of horizontal weak tableaus, such kind of crystal theory has not been available. So we had to devise this part for ourselves, but we could find a way to introduce a leading map, and then we could arrive at the formula. Yeah. So then, yeah, this is an example. So we do apply this column version of RSK, then we could arrive at separated paths. Then we can lead off the horizontal weak tableau, as in the case of VSTs. Then there's a very similar analogous bijection, and related Cauchy identities here, and you can also consider the restricted sum. And this is what I explained verbally, I think. So yeah, but in this case, so after applying the leading maps, the leading tableau becomes consisting only of the number ones. And the weakly horizontal tableau with this only ones, you can simply project it to this first row. Then it becomes a particle configuration. And if you look at the dynamics for this is identical to BBS, right? This is the situation. Okay, anyway, so this is the end of my talk. So yeah, so this is a kind of non-fact. Stochastic vertex models are related to q-Whittaker measures due to a few works of people in this audience. And this is not apparently, at least, not free fermionic. We have found biject relation from the q-Whittaker measures to periodic Schur measure, which is really free fermionic. And this was achieved by what I explained. This is Skew RSK dynamics. And this is, to give a proof, we needed the theory of affine crystal. And we have also introduced a column version of Skew RSK. And this shows a nice direct connection to the theory of BBS. Thank you very much for your attention.